Hello people! What is this diagram trying to show us? Well, it's just showing that two masses will exert gravitational pulls on each other. And this formula here, what is it called? Is the law of universal gravitation. What it says is, if you have 2 point masses separated by a distance d, then the force of attraction between them is proportional to the product of the masses, but inversely proportional to the square of the distance between them. This is the constant of proportionality. It's called the gravitational constant, and it has this value here. Now you only know whether you have understood the formula if you can apply it properly, yeah? So let's try it on the situation when we have two bowling balls, 3.6 and 7.2 kilograms, touching each other. So we are going to calculate the force of attraction between them. So let's bring up the formula. Okay, m1 times m2. So should I do 3.6 times 7.2 or should I do 7.2 times 3.6? Doesn't matter, right? Doesn't matter. So this reminds you of the third law, isn't it? I mean the Newton's third law of motion. The force of attraction between them is an action-reaction pair. So even if one of them is smaller than the other one, they are still going to exert equal but opposite gravitational pull on each other. So the Newton's third law is actually embedded, yeah, in the law of universal gravitation. Next thing, what about d squared? What is the distance between them? I said that we want the two bowling balls to touch, right? Does that mean that we're going to put 0 square here? Which would mean that the force of attraction is infinitely large. Something is wrong, right? It cannot be 0. Now, the law of gravitation is actually between 2 point masses. Bowling balls are definitely not point masses. The mass is distributed over a big volume. But it's okay, we can just pretend that all the masses is concentrated at the center of mass of the bowling balls. So the distance between these two bowling balls is not 0. It should be the center of mass to center of mass distance. So for bowling balls, it should be roughly about 22 cm. So the denominator here, we are going to put 0.22 square. Use your calculator, you get this answer here. Now this is a tiny force, yeah? I think even a mosquito landing on the bowling ball will exert a larger force than this. Of course, this is due to the gravitational constant being such a pathetically small number. That's why to have meaningful gravitational pulls, at least one of the two masses must be a gigantic mass. Okay, let's replace one of the bowling balls with planet Earth. So we want to calculate the gravitational forces that the planet Earth exerts on a 10 kilogram bowling ball. Now again, what should be the distance between them? It should be the center of mass to center of mass distance. So the radius of the Earth is roughly about 6,370 kilometers. The radius of the bowling ball is just a few cm, which is really negligible compared to the radius of the Earth. So when we apply the formula for the distance between them, I'm just going to put the radius of the Earth. I'm just going to ignore the few cm here. Use your calculator, you're going to get the answer 98.1 newtons. So the Earth pulls the bowling ball down with a force of 98.1 newtons. Remember, it's an action-reaction pair, so the 10 kilogram bowling ball pulls the Earth up with a force of 98.1 newtons. Don't you think this number look very familiar? Have we seen this number somewhere else before? Now, if you know the answer, why not leave it in the comment section? That's all. Ta-ta!